All right, good afternoon. Hey, I just saw your note that looks like yesterday's video got cut short. That's very weird. Yep, sure enough, 12 minutes. All right, well, I don't know where that happened or why that happened, um, except that yesterday was a really bad day for my technology because I kept having all kinds of things fail. So, but we will be talking about PA3 multiple times. Um, so let's start with questions. Anything in particular you want to talk about PA3? Any parts of it that are particularly unclear? Or questions on anything? Well, I kind of expect that a lot of this needs to be gone over more than once anyway. Um, Even if we went over it yesterday. So general structure. You want to implement binary trees, um, and so you're definitely going to have some kind of tree class, and your tree is comprised of nodes, so you're going to have some kind of node class, and you're going to have your main class, and that may be all you need. 3 classes. So your main pa3.java that has your main class, and then tree.java, node.java, and those can be set up the way we did. Over here, tree 1. Alright, so your tree class is basically a wrapper around your node class. So because we do all our tree stuff recursively, well, we're really just doing some of it recursively, but because trees tend to be recursive, right, we need to be able to from, say, a traversal method, call the traversal method on a subtree. And our root is a node, it's not a tree, right? Our root is a node, whereas the tree is, the thing that holds the root and the other methods. So our traversal methods will usually just call the corresponding traversal method on the root node. Our add method would call the add method on the root node. A search method would call the search method on the root node, and so on. So the tree class is kind of a wrapper, and the node class is what really does the work. So our traverse code, for example, right, if this is an in-order traversal, left node, right, if there's a left child, call print on that left child, right? So left is a node, and so it has a print method, and then print the root node's data. That's just an integer in this case, and then if the right is not null, call the right node's print method. And the real difference from, one of the big differences from 222 is, we need to manage this stuff ourselves. We're not calling print and passing a node to it, and the print method can see if that node is null. We're calling the print method in this right subtree. And so if write was null, saying write.print would give us an exception. So we have to do these checks before we make the recursive call. But the basic structure of the recursion is the same. And then, in this case, binary search tree, the way we use the tree class is, construct a tree, add some things, print. And we do all of those things on the tree, and the tree methods basically just punt to node methods on the root node. So that can give you a starting point for cobbling together a tree class. And so we're going to have trees and nodes. And what do we need to do? We need to play the game. We need to read the tree in from a file. We need to write the tree back to the file. And those are sort of the three top level things, right? So ingest happens once and only once at the very beginning. When you first run the program, you figure out what file you want to read over and just ingest from there. And then play the game, and at the end, if you had to make an adjustment to the tree, write the tree back out to the file. Play the game. If you win, don't worry about it. Play the game. If there's an adjustment to the tree, adjust it, and then write it back out to the file. So make files. So you can do a make file for this, but usually you don't have to. Usually if you just compile your main program, it will compile the subclasses. Or, honestly, if you're doing one project per directory, I usually just javac star.java. Or, if you change tree.java, just javac tree.java. Just compile it as you're making edits. But if you need something fancier, you can do a makefile, and it's just javac instead of GCC basically. All right, so let's go over adjusting the tree, and then let's look at ingest again. Now these methods, where they belong is a decision that you need to think about and make. You may want play the game to be part of the tree class. You may want it to be part of a node class. You may have it just be a method in your main program, but probably not. It probably belongs in one of these classes. Ingest, you might want an ingest method in the tree class that calls an ingest method in the node class. And so on. Write tree you can probably put in the tree class. But let's talk about the details of what these look like. So let's update the tree. So suppose we have our tree. I'm just going to call it tree. And I'm going to define a pretty simple structure, which is going to be a Boolean question flag. So this will be true if we have a question, false if we have an answer. A string which holds the text of the question or the answer. A node called yes and a node called no, which are the two children of a node. So if we have a question node, this will be true, this will be the question, and then these will be the branches that you go to for a yes or a no. If we have an answer, this will be false, this will be the answer, and these will be null. Alright, so suppose your tree looks like this. Here's a question. Is it alive? Here's a question which says, is it furry? Here's an answer which says it's a cat. Here's an answer which says it's a rock. Here's an answer. It's what's a non-furry thing that's alive? It's a tree. And here's an answer which says it's a rock. This is assuming rocks are not alive, which I wouldn't assume. To play this game, right, we're going to start at the root. So something like, temp equals root. And well, temp's Q flag is true, meaning that this is a question. So while we have a question, print the text, get yes, no response. If yes, set temp equal to temp.yes. Else temp equals temp.no. And go back up to the top. Alright, so this plays the game. This moves down. It lets you say yes or no until you get to something where the Q flag is false, which means it's an answer. And so at that point, you know, print answer. And if your answer was correct, then we're done. We played the game and we won. No need. Alright, what happens if the answer was incorrect? So let's say we got down to here and we said, I know what you're thinking of a tree. And we're told, no, I was thinking of an ant. Okay, so give me a question for which yes is an ant, no is a tree. Is it very small? Right? And so we would build a new question node which says, is it very small? The yes node would be an ant, the no node would be a tree. Alright, so how does that work? We need the following. We need to know the identity of this previous node because it's one of its children that we're going to adjust, right? And if all we have is temp is equal to this, we can't change temp to be the root of a new tree because that doesn't change this node's no child to be that new node. So we need to remember the previous node, right? So before we move down, let's go ahead and say, you know, previous equals temp. And we also need to know whether the last movement that we made was on the yes side or the no side. So in addition to saving, you know, our previous node, we're going to remember this direction. So in addition to saying temp equals temp.yes, I don't know, I'll say previous dir equals 1. Or previous direction equals 0. Or something, you know. Some flag to tell you whether you went this way or that way. Alright, so what happens when we play this game? We start off here. This is going to be a question, we're guaranteed. We'll say, is it alive? The person says yes. So we'll set previous equal to this node. We'll set temp equal to temp.yes, so this is temp. We'll set previous direction equal 1. I'm gonna go symbolic on here. So some value to represent no or yes. Let's do that. So, you know, make a constant called yes or something like that. So at this point, our previous direction is yes. Our previous node is right here. Temp is equal to this. Okay, so come back up to the top. This is a question, so we're going to ask the question. Is it furry? The person says no. Okay, so we're going to say temp equals temp.no. So this is going to be temp. We're going to set previous equal to what temp was, so previous is right here. And we're going to set previous direction to be no. And we're going to come back up to the top and we're going to say, is our current temp a question? And it's not. So we're going to exit from our while loop. Okay? And we're all set up with everything that we need. Okay? Temp is the answer that we're going to guess. Previous is the node that we came from. Previous direction tells us which way we traveled from that previous node to get to our final answer. So we print our answer. I think you're thinking of a tree. Was I correct? person says, no, it was not a tree. Okay, what was it? It was an ant. Okay, give me a new question. So our new question is it small? The new yes answer should be an ant, which is what they were thinking of. The new no answer should be a rock, which was what we guessed incorrectly. Yeah. So make yourself a tree, right? Make a node that's a question node. Is it small? Set the yes side to an answer node that says ant. Set the no side to an answer node that says rock. And now go up to your previous node and set either its yes or no child equal to this. Which one do you do? Look at your previous direction. Our previous direction was no. So I'm going to basically say previous dot no equals, I'm going to set it equal to this new tree that I just constructed. And the effect of that is this now gets replaced with a question. Is it small? On the yes side is an answer, which is an ant. On the no side is an answer, which is a tree. Presumably not a baby tree. Right? So as you're playing the game, as you're moving down, you just need to keep track of two pieces of information. Each time that you move either to the yes or no child, remember the node you're moving from, which I'm calling previous, and remember which direction you moved. So make yourself a flag, you know, last move was in the yes direction. Set it to true if you went yes, false if you said no, or something like that, right? And then you can use that to adjust the previous node's yes or no child to be your new tree. So that constructs the new tree for you, and then when you're done, just write it out by doing an NLR traversal. Open a print writer for the database file, and instead of system out print, do printwriter.print or print line. Alright, so that's the tree update algorithm. Let's do another look at ingest. So after you've written this out, you've got a text file with questions and answers. So read tree, which you can call with a file name maybe. So open a scanner, which I'm just going to call SC. When you open a scanner on this, there's a file pointer maintained by the scanner which says I'm about to read this line. If someone calls next line, this is the line I'm going to give them. And then I'm going to move my file pointer down. Alright, so the ingest method takes in that scanner and probably returns a node. Ultimately it's a tree, but a tree is really just, you know, a root node. So we'll probably do this at the node level. And this is the algorithm that we've been talking about. So so read line, read two lines. Everything's done in groups of two. If it's an answer, make an answer node and just return it. So if you were sitting right here and you called ingest, You would say, oh, here's an answer. It's an upside down uh, dollhouse. And so you create a node which says this is an answer. The text is upside down dollhouse. The yes and no children are null, and you return that, right? But if you're sitting right here and you call ingest, right? So if it's a queue, make a node with that text, which will be a question, and then set your yes subtree equal to the return value from ingest, and then set your no subtree equal to the return value from ingest, and return that new tree. This is hard to sneak up on. It kind of works or doesn't work, but it's usually not too bad to get it to work. But if it looks like it's doing the right thing, it's probably doing the right thing. Now, how can you tell? Well, you know, you could try to ingest and build a tree from a file, and then just go ahead and traverse it and print it out to your screen and see if it looks reasonable, right? Or if you already have your gameplay method written, you can go ahead and play the game on it. But one way to know if this works is when you call ingest at the beginning here. So we should have had a line up here in the beginning which said ingest. Right, and that should return the root of the entire decision tree. When you get back from here, you should have read in exactly the last line of your input file. So this should have, you know, as many nodes as you have in that text file. And if you just start printing out this thing in like node left right, or even left node right, you should be able to tell if you got the right tree structure. So yeah, to start with a tree class. Update your node to hold a flag and a string of text. Call your children yes and no. Put together a simple tree by hand. Just hardwire a basic decision tree like this. Bunch of assignment statements. And then I would say work on the play the game method. And try not to worry about ingest. Try not to worry about writing back to disk. Try not to worry about updating the tree at the end. Just worry about, you know, I'm going to do a bunch of assignment statements to make this tree in memory. Just, you know, hand wired. And just worry about one method for playing the game. Right? If you can get that working, you're more than halfway through. One method. Right? And it's one task to focus on, and it's hard sometimes when you're programming. There's all these other things out there you know you're going to have to do, and if you're anxious about it, you want to go off and work on those as quickly as possible, right? But I think it's productive sometimes to get something working, right, and then start building on that. So just take one task, just write something that'll play the game given a decision tree. And it doesn't matter how you structure that for a first pass. You can just make it a method inside main. You can, you know, have something you pass a tree to it, or you can make it a part of the tree class. Doesn't matter, right? You're just trying to get the logic down, get yourself to where you can actually go through the tree, print the questions, get responses, right? And get down to an answer that's either correct or incorrect. And if you get that and you get that working and you get some comfort with that, then building on top of that is not as intimidating usually as kind of starting from scratch and looking at this and saying, what the heck does that mean? How am I going to update this tree? What's this previous dir, right? Don't worry about that. Leave it for later. Get something working first. But try to get something working first soon, right? This week, today or tomorrow. And, you know, be coming into office hours or asking questions in class and so on. So that hopefully by the weekend you can play a game from a hardwired tree. And then you can start working on the next parts, right? But like I say, once you get this working where you can just play from the root down to a leaf node, you're at least halfway done. All right, we can change gears here. Let's talk about class extensions. So this is something we're going to do a lot of. We already do some of this, and we're going to use this mechanism quite a bit. So here's our rectangle class, right? It's a thing, an object with a length and a height. There's a constructor. Oh, let me get rid of the word this. Okay, you didn't see that. All right, so we've got a length and a height. We've got a default constructor, and we've got an area method. Yeah. We've got an area method that just returns the area, and we've got a toString method, right? So that's our basic rectangle class, and it's fine, it works, you know, we put it out for sale, and people give us millions of dollars for it, and that's all great. But then, you know, next year we need a new product, right? So we're going to invent, you know, a new type of rectangle. So we want a better rectangle, which will also include a perimeter method, because people like to calculate the perimeters of rectangles. So we're going to create a new type of rectangle class. We're going to call this you know, rectangle 2. So we want a class rectangle 2, so we can say rectangle 2r equals new rectangle 2. You know, maybe put some dimensions in there. And this new kind of rectangle has a perimeter method. Yeah, and I called it a super rectangle this morning, and that became confusing, perhaps. So let's make this. So we'll call this main2 appropriately enough. Alright, so we'll make a 5x7 rectangle. And we'll print out what r is equal to. And we'll print out its area. And we'll print out its perimeter. And, you know, if I try to do this with a plain old rectangle, I'll get a compile error. Or an error because I put in an extra quotation mark. Alright, so I get a compile error, also because of typos. Alright, there we go. Alright, so it doesn't understand perimeter, right? It's not part of the rectangle class. So we're going to make a new rectangle class that's going to include a perimeter method. Now, we've got a few choices for this, right? If we have the source code for a rectangle, which we do, right? We could just take all of this and put it into our rectangle 2 class and then add a perimeter method to it. But that's a lot of work. We may not have the source code to this. And we don't need to do that, right? Rectangles already exist. So what we're going to do is we're just going to create a rectangle2 class, and I'm going to say this extends a rectangle. And what I'm going to put in here is some extra stuff. Now this extends keyword basically says rectangle2 is everything that a rectangle is. All of the methods, all of the fields, all that stuff that's in a rectangle, that's now a part of rectangle2. But I can also add stuff to this. So I can say public integer perimeter. And there's a perimeter method. And so now my rectangle2 it should know what this perimeter method is. Alright, so this is about code reuse. This is about not having to rewrite everything that's part of a rectangle just to add one more method to it. Or to change something. Suppose I want to change my area method to multiply my area by 144 because I want my area to come out in square inches and I want my construction to understand feet. Right? So I might want a new area method. That would be a bad thing to do. But you know, if I wanted to do that, I could rewrite the area method and it would override the area method in the rectangle class. So this is called the base class, right? Or sometimes a super class. That's the thing that we're extending. This is a new class we're defining. Alright, so there's one detail that we still need to deal with, and that's the business of constructors. And constructors, Java does this in a little bit of a peculiar way, maybe. I need to actually define the constructor for this extended class. Even if I just want the same constructor that I had in a rectangle, I still have to explicitly define this. And there's different ways to do this. So let's make a public rectangle2 with a length and a height. Right, so there's our new rectangle 2. It's a 5 by 7, it has an area of 35, but now we can talk about the perimeter. And it's 7 plus 5 times 2. I still have the area method, even though I didn't define an area method in here. I still have a toString method, even though I didn't define a toString method in here. Right? It inherited those in some sense from the rectangle class. Alright, so far so good. So extends is a keyword. The next keyword is super. Yeah, this I would consider this inheritance. But I think that word probably means different things to different people. Alright, this constructor is interesting, right? I'm doing exactly the same thing that I would do in the rectangle constructor. So there's a keyword super, and super is a way to get access to this base class. And so for my constructor, instead of repeating the code that I have here, I could have actually said super L comma H. And that'll actually call the constructor in the rectangle class. Oh, that was weird. Yeah, so what did just happened here? Oh, yeah. Sorry, I changed this for the morning class. All right. So you didn't see that. Um, so I'm constructing my rectangle 2 by calling the constructor in the rectangle class. So that's what the super keyword is doing. And super is a general keyword. All right, so we have confirmation. Yes, extending is inheritance. Cool. Thank you. Super is a general keyword if you want to get a hold of something from this base class, rectangle in this case. Now, if I just want to you know, access something in there like length, right? I can just say length, right? And length is a field. I can just call it length. But if I override something, for example, suppose I write my own toString method. Right, so I'll change my toString method to just laugh at us. So now when I print out my rectangle, it says r is equal to a ha ha ha. Right? What if I wanted to, in some cases, use the original toString method? So I might do something like this. If the length is 1, I want my toString method to return ha ha ha. Otherwise, I want to return a string that says, you know, a length by height rectangle. So I can get to the original toString method by saying super.toString. Like that. And that'll access the toString method in the rectangle class. If I just say toString, I'm referring to this. And out here, when I say something like, let's print out the value of r, right, by concatenating it to a string, let's turn this into a string, it's calling this method. But if my length is not equal to 1, then I'm going to go ahead and call the original rectangle class's toString, which should give us back this form that we're familiar with, where it looks like this. All right, so there's our usual behavior. But if I change this to be a 1x1 rectangle instead, right, then it says rectangle is a ha ha ha. Oh yeah, and good clarification in chat also. If you're going to use the super keyword to call the super constructor, for example, it's got to be the first thing in your method. That's another sort of peculiarity. And if you don't make it the first thing, you'll get an error message saying super has to be the first thing. So it's pretty explanatory. All right, so that's a keyword, super. And super, when you're doing a class extension, super refers to the class that you're extending. So we can get to methods and fields in there. Okay, there's another keyword, and this one I don't like talking about because it gets misused way too easily. But it's probably a good time to talk about it. And some people have already discovered it, you know, you hear things on the street. So that's the keyword this. All right? And it's hard to talk about in English because we use this in sentences, but this is a very interesting concept, the keyword this. This is the notion of self. It's the ego. It's I. It's something that you can use in code to refer to yourself. So what does this mean? For example, suppose I have a rectangle R and I say r.area. We know that we're going to start executing code inside the rectangle class, and it's going to start running this area code. Inside this code, if I use the keyword this, it would refer to the object R. If I have a new rectangle that I call R17, and I call R17.area, then right here in this area method, if I use the keyword this, it refers to the object R17. Okay, so this is, it's me, it's myself, right? And that's a little bit of a weird thing. And we don't have too much need to use it right now. We are going to need to use it in PA5 most likely. But there is still one case where we'll often see it used, and that's in constructors. Yeah, exactly. So when we made this constructor, right, it's called rectangle. It takes two arguments, a length and a height. And then I want to set length equal to L, height equal to H. So what is length? It's a variable defined globally, if you like, in this class, right? Anything that refers to length is going to refer to length right up here, this integer, right? Unless I define some local variable length in here, in which case, if I say length, it'll be that local variable. So for example, down here in the toString method, let's say I want to multiply my length by 12, right? I could say integer length, right? Well, now when I say length, I'm referring to this variable. That's the scoping rules that C, Java, most languages share. So if this is a local variable in this method, that's what length refers to. Okay, but up here, I don't have a local variable called length in this constructor, so length refers to this. But, if you're writing good code, you don't want to use variable names like L and H. Because you look at the constructor and what is L, what is H? Well, maybe you remember L is length, H is height, right? But if this is not something like a simple rectangle, and if it's got 15 arguments to it, you'd like to have meaningful names. So really, to make this thing, easier to read and work with and less error prone, I'd like to say this. I'd like to call these things what they are. Which means that this statement now looks like this. And this is a silly statement, right? Length equals length, that doesn't do anything. And that's not really what I meant. What I really wanted to say was take this value of length up here, this variable that's part of the class, and set that equal to this local variable, which we got as an argument. This length is different from this length. This refers to the one that's part of the class. This refers to the local variable that was passed as an argument. This height refers to the height that's defined up here as part of the class. This height refers to this argument. So we need a way to be able to specify the length that's part of the object in this case, and that's what the keyword this does for us. So if we write this dot length equals length and this dot height equals height, it's doing exactly what we had before without having these artificially strange names like L and H. So this is saying this dot length, that's this thing right here, should be set equal to length, which is that thing right there. So it copies this argument into the class variable's length, and it copies the height into the height. So this is a more proper and typical way that we would write a constructor like this. But don't get carried away with this. Right down here, I do not need to say this dot length equals this dot height equals 1. Because if I say length, that can only refer to one thing, the length right here. because I don't have a variable inside this constructor called length. So this is completely unambiguous and correct. Now if I say this dot length equals this dot height equals 1, that's also correct, but it's needless, right? If I say return this dot length times this dot height, it's going to do the right thing, but it's going to look like you don't understand the keyword this. So we really use that keyword when we need to differentiate between, say, a local variable of this name and the variable with the same name that's part of the class structure. And yeah, you can do multiple equals on one line. Turn off your spell checker. I really don't think I feel good about editor spell checking me while I'm typing code. It just feels like something else is going on other than writing code. All right, so that's the this keyword, right? Now we'll use this in more interesting ways, because at some point we may find that we have an object which is executing some code, and it needs to tell some other object about itself. And so we may call a method in another object, and we may pass an argument like this, which means, you know, here's a copy of me, or a reference to me. And this is how we can have objects, you know, sort of find out about each other. We'll do some of that when we're doing threading. We'll do it when we're doing GUIs and stuff like that. So we'll have plenty of opportunities to do that. All right, so those are some keywords, and we'll revisit them as we go forward. But this is all basically set up to class extensions. We're going to start moving towards doing some GUI work. So we're going to start making widgets that you know, pop things up on our screen and give us buttons to click, and things we can type in, and reactions to mouse events, and so on and so forth. Now, as part of that, we're going to start moving into an IDE. And so we're going to work with Eclipse. All right. Now, I'm not anti-IDE, but I generally don't use integrated development environments, except for Arduinos, because, you know. But the reason we're going to use an IDE for PA4 and 5 and for doing GUI stuff is that if we want to make a window pop up on our screen, right, take a look at what a window contains. You know, there's a background, there's a border, there's a thing on the top here, there's a very high thing on the top that we can grab and drag, there's little buttons here we can use to minimize, maximize, or close, there's a button over here we can click on to do some other things, we can grab a corner and resize, and so on and so forth. We don't want to write code to do all of that stuff. So we're going to take some existing classes like JFrames, and we're going to extend those. And we're going to add the details of what we want our graphical device to do. So you're going to be doing class extensions. But even with, you know, starting with something like a JFrame and extending it, it's going to take a lot of work to get, you know, a basic window up with some buttons and a drawing area and stuff like that. So we're going to use a drag and drop system for making these graphical devices. We're going to use something called Window Builder. And Window Builder works pretty well under Eclipse. And the effect is going to be we're going to drag and drop things to create, you know, a visual element. But every time we drag and drop something or resize something or change the color of something, it's going to generate a bunch of Java code for us. And we're going to get a huge chunk of Java code without ever touching the keyboard, right? Just by dragging and dropping and placing components and configuring our interface to look a certain way, this tool will build a lot of code for us. And I want to spend our time in this part of the course using these objects rather than learning the low-level details of how to get these objects to behave or look a certain way. So we're going to use IDEs from here on out, and we're going to work with Eclipse. We're going to use Window Builder to help us create these graphical objects. And then we're going to concentrate on linking the behavior of these objects to code that we write, so we can respond to mouse clicks, button presses, things like that. So tomorrow I will load up a completely from scratch version of Ubuntu in a virtual box, and we'll go ahead and we'll install Eclipse, which will bring in Java. We'll install Swing, which is what we're building on top of, and Window Builder, which will use Swing. And I'll go through that process from start to finish. You're encouraged to play along while we do this tomorrow, to get this set up on your own system if you don't already have a system that works well. If you already have, Java 11 installed and some other stuff, you may want to make yourself a virtual box to work with these particular versions of things. You can try it, but some of the stuff is pretty finicky, and it varies from month to month. So last time I tried this, what I'm going to do tomorrow seemed like it worked pretty well. But if it doesn't work for your system, you may want to just virtualize and do PA4 and 5 in a virtual box. All right, we are out of time. Enjoy the afternoon, enjoy the sunshine, and I will see you tomorrow.